If the gearbox at A is frozen, what is the angle of twist at D in degrees? So we take a look at this here, and I've got a shaft that's spinning. It's sitting in this bearing at D. I've got these flywheels where I'm applying torque at point B and C. And so what happens? The gearbox freezes up. All those forces are still there. It's still trying to spin it around. So let's figure out how far that it spins around. So the very first thing that we have to do is we have to figure out what the internal torques are. And so if we remember back from our statics class, when are the torques going to change? The internal torques are going to change every time an external torque is placed on. So if I draw a free body diagram of my shaft here, basically if the gearbox freezes at A, that's a grounding condition. I have a torque being applied at 1, I have a torque being applied at 2, and at D, it's free to spin because we're looking at a free riding bearing situation. So it doesn't matter which way that we deal things. So I will have some reaction torque, and so we'll call that the torque at A. That's going to be opposing these other torques. So this is my free body diagram. And so I will be able to say that, okay, if I look at that, the torque at A is, and actually let's do this a little more formally, the sum of all the torques counterclockwise is positive. These have to be equal to 0. And summing the torques is the same thing as summing the moments in this case. So as I look at it, my torque in the A direction is negative, and then that's going to equal to plus T1 plus T2. So our free body diagram tells us that the torque, the reaction torque at A, is going to equal to the torque 1 plus the torque at 2. And we do have values for those, so we can sit there and go, okay, well, that means the torque at A is going to be 20 kip inches plus 12 kip inches, so the torque at A is 32 kip inches. Okay, now at this point, our free body diagram is done. Now we have to figure out what the internal torques are, because that's the important thing. So, internal torques will change every time the external torque is changed. So if I sit here and look, if I make a break here, and I can go anywhere in that shaft between the one torque and the other torque, I'll have a torque value. I'll have to take a look there because I apply the torque and it's going to change, and I'll have to take a look there. And so as I look at these, I can draw a free body diagram of the three of these. It does not matter in which direction that I go from. I can work it from the grounded end out, or I can work it from the free end in. I'm going to get the exact same thing. So if I draw a free body diagram here, if I draw a free body diagram here of the shaft, failing at writing today. So if I draw a free body diagram of the shaft, there's the first cut, there's the second cut, and there'd be for the third cut. So I'm just kind of just drawing the shaft with my different cuts in it. So I look at it, my external force, all these guys are going to be that TA. And since I'm cutting it before T1, this first one's going to be done. Second one, I'm going to have T1 on it, and then the third one I'll have T1, and then I'll have T2. Okay, so taking a look at those, we got to figure out the internal torques in all these places. And so if this is TA, the internal torque has got to be equal to TA, pushing back that same distance. And then if I've got TA and then T1, what's this going to be coming back here? Well, this is going to be TA, because that was positive, minus T1. That will be the quantity of the internal torque. And then here we're going to end up with TA is T1 minus T2. So if I look at all of these, it tells me that in this first one, I'm going to have 32 kip inches, because that's what it's going to take to balance it out, to keep everything in static equilibrium. So if I go to the next one, what's the next one going to be? Well, it's going to be TA, which is 32, but I'll be taking 12 off of that, so the force here is going to have, excuse me, I'm going to be taking 20 off of it because T1 is 20 kip inches. That means this is going to be 12 kip inches. And then if I go to the third, the free end, TA minus T1 minus T2, that's going to tell me it's going to be 0, which should make sense because it's free. There's nothing to twist it. And we get the exact same thing because if I started building my free body diagrams from the other direction, and I'll just do the first one here, well, there's the free end. And before we apply any torque, well, there's no torque in it at all. So this is a case of, there is no internal torque in that section from C to D. So as I'm looking from here to here, well, that's a bad highlighter color. But as I'm looking from C to D, there is no internal torque. So what does that tell me? There is no angle of twist between C to D. There is no stress in C to D because we have to have an internal torque to have a stress and have a dimensional change. So now we've got all of our torques figured out. Let's actually go and calculate out what the angle of twist is. So what is angle of twist? Angle of twist is the sum of all the TL over JGs. Now, as I look at this, so that's going to be TL, JG, A to B, B to C, C to D. Now, we know a couple of things about this. The diameter doesn't change the entire way through. The material doesn't change the entire way through. So what I'm going to do is I'm going to try to make this a little bit easier on myself. So this is going to be 1 over JG because each individual part is JG. And then I'm going to have T AB LAB plus TBC LBC plus TCD LCD. And so that's going to give us our angle of twist all the way through. So 1 over JG, what is J? We have our diameter of 3 inches in the initial one. So that's pi over 2, 3 inches raised to the 4th. There's our polar moment of inertia. And we have G. G is given to us as 11,500 KSI. I'm just going to turn that into PSI because KSI is just 1,000 PSI. And then we go, okay, TAB. So the amount of internal torque between A and B is going to be 32 kip inches. So what is a kip? A kip is 1,000 pounds. So 32,000 pounds times inch. So the next question is the length. What length do we use? Well, it's the length over which we have that 32,000 pound inches acting. And so that's just going to be over that first length, because as soon as we add the new torque to it, the internal torque is going to change, and that's going to mess everything up. Not really mess everything up, just change everything. So that first length is 20 inches. Okay, and we're going to add to that. What's the torque in BC? Well, the torque in BC is 12,000 pound inches, because we already calculated that out. What is that? Over which length does that work? It works over that second length of 30 inches. And now, just for completeness sake, we have 0 pound-inch torque in that last one, and that 0 pound-inch acts over 20 inches. Yeah, we don't need this in here, but like I said, just for completeness sake, I want to throw that in. So now I have all of this. I just plug it into my calculator and see what it spits out. So that's going to tell me the angle of twist, and it's going to be 0.0109. Now that's going to be in radians, because that's the units that we're based in. So, but we want it in degrees. So what do I have to do to get this from radians to degrees? Well, I have to go that there are 360 degrees, and a circle is 2 pi radians. So that's my conversion factor. And then once I do that, I'll plug that back into my calculator, I'll find out 0.627 degrees is my angle of twist when the gearbox freezes.